Hey folks, welcome back to another Geometry Nodes tutorial. In this one, we're going to be having a look at how to create our very own Curve Deform node group. That looks something like this. If you have a mesh where you have enough topology, doesn't really matter if you do have enough topology, but it certainly looks better if you have more, and you have a curve of some kind like this, then what you can do is grab your mesh object. I'm in Blender 4 here, so we're going to just grab our new Curve Deform that we made previously. And now you can see I can move this around on my original curve. As I rotate it, you can see there's some rotation there. This is going to be defined by information about the curve itself, because we're basically following information from that curve. I can still do things like Control T to set tilt, and I believe it is Alt S to set radius. So you can see that we have a fully featured Curve Deform happening here. This is one of those nodes which is just super useful if you want to be controlling stuff with geometry nodes. When working procedurally, it's often fairly straightforward to actually build out the skeleton of something with curves, because you simply create the contours or the ribs of something, and then we can create our meshes along them. What this does mean is that we want something which is a little bit more intelligent than, for example, if we were to add just a deform curve modifier. Curve modifier itself takes a single curve, a deform axis, and a vertex group of the mesh you're deforming. In our case, what happens if I have 100 curves, 1,000 curves, because I've procedurally generated them and I want to assign specific meshes to different curves, and I want different tilts and radii, and you can expand this later as well to do different axes depending on which spline you're looking at. Geometry nodes really opens up a huge amount of possibilities.
Just before we get too deeply into Blender here, quick word from today's sponsor, Pidgeon Tools. They've just released the Pidgeon Toolbag, and this is a collection of utility add-ons designed to make your life a little bit easier, give you a bit more time to work on your artistry, and let the admin side of Blender take care of itself. This is a free add-on, and there's just been a huge amount of work that's gone into it, so I definitely recommend it. Check the links down in the description below. So what's included? Well, if we have a look through this main features, you can see that each one of these is essentially its own add-on. They all get installed as a bundle, and it makes it easier for you to update them as well as a bundle, and they all work seamlessly with one another. So we have the Super Image Denoiser. This is kind of the most famous one, I think, from Pidgeon Tools. What this does is it massively increases the quality of denoising in Blender. And another thing which is really fantastic about this, if you're an animator, is that they include temporal denoising, so it improves the denoising quality and reduces flickering throughout an animation. Having better denoising means that you can have fewer samples, means you can render faster. Talking of rendering faster, we also have super fast render. This is going to automatically benchmark and optimize your scene to improve your render times. And if you're working on slower hardware, this is potentially going to be a game changer for you with whether you can or cannot actually render a project. Still looking at the render stuff, we have Super Resolution Render. This is going to be an add-on that allows you to render things which are massive in terms of your pixels. For many of us, our PCs can't actually render above a certain size, or the tiles or the GPU runs out of memory, or something will happen where the hardware simply cannot deal with rendering. Well, this add-on is going to allow you to automatically cut up and render individual tiles, and then it's going to restitch them for you. If you have a few different PCs, you can also set up your own render farm using Super Render Farm with your own networking and nodes on there. One of the add-ons which I like most, use most, is the Project Manager. I really love having a very specific folder structure and keeping my images and references and blend files very organized. And the way that I like to do this is through the Super Project Manager, which is going to allow you to define a project structure, a folder structure. And then when you're working in Blender, you can initialize this project and then start working in it seamlessly. All of those folders are going to be created. Your, for example, like your render image output directory, that is going to be defined as well for you. Really just irons out a lot of the pain points of working on bigger projects. There's a few add-ons here as well, which are still in development or coming. And these are the super organized nodes, which are going to improve your node networks. Super real sound. This is going to improve your sound interactions. Super easy analytics, which is still in planning. And this is about tracking time and performance. And then there's also more coming in the future. This is a crazy bundle, and you can get it for free. So check the links down in the description below and enjoy.
I've got a brand new version of Blender 4.0 beta today. There's a few changes with 4.0, so that's why I'm using it rather than 3.6. Feel free to follow along if you're still in 3.6, but I think it's good to get the exposure, get the practice with the new version. Let's start off by setting up our scene. Go ahead and add a cube in here, and we want to add a huge amount of topology, not a huge amount, but some more topology. So go ahead, let's add our modifier. We have this new menu in 4.0, and you can actually just go straight away and start typing to search. I want to add a subdivision surface modifier. Otherwise, you're just going to add, generate subdivision surface. I don't want to change the shape. Let's go for simple, and I'm going to turn off optimal display so that we can see the cuts, and let's see how many we want. Something like 4 is going to be fine for us here. And then I'm just going to hit Control A to apply. So this is just giving us enough topology so that as we work with deforming this along the spline, we're going to be able to actually see it curve along the spline properly. If we just use the default points, if we just had a cube like this and we were deforming it along the spline, then we would simply have our first 2 points here, our final 2 points there, and it would stretch the middle. So that's not going to be indicative of this working correctly. So we want to make sure that we have enough topology to debug the system as we're working. Now, the other thing that we're going to need here is a spline. So go ahead and add a curve Bezier, and I'm just going to scale this up a bunch like this. I'm going to go Control A, apply rotation and scale. One thing that you may not know about curves is that when you apply the scale, having scaled it up, you will also be applying the radius at that new scale. So you can see that my mean radius is 10.6 because the whole thing has just been scaled up. What I'm going to do is I'm just going to set this back to 1, and that's going to make sure that our radius on all of those points, which is only 2, is back to just a standard 1, a normalized size. This is going to be important because later we're going to use the radius to control our deformation. I also like to add a separate object for my geometry nodes here. So I'll just add this, geonodes, and it just allows me to import different objects to test out different things as they're deforming in case I want to debug with a different thing. Maybe I want to do an array, maybe I want to do a collection of objects, just more options. Let's create a new geometry nodes modifier, and this one we're going to call Curve Deform. And to begin with, we want to bring in our cube that we have subdivided and our Bezier curve. So drag both of these in. Our Bezier curve we're also going to set to relative just to make sure that we are using the points that we see, just to make it as intuitive as possible. We should probably start with a bit of theory just to make sure that we're all on the same page about what a curve deform is actually doing and how we can approach thinking about it. So what curve deform is actually doing here is we're taking our cube, or any mesh for that matter, and we're remapping it from a standard X, Y, Z Cartesian space. And when we say Cartesian space, we're just talking about a linear 3-dimensional space. If I go 1 meter in that direction, then my coordinate has increased by 1 value. This is very slightly different from curve space, which is what we're going to be moving into. So curve space is not necessarily linear. Things are not in straight lines. They follow the curve. We still need 3 axes along our curve. If you know anything about curves, 2 of these very straightforward to get. We have our curve tangent. This is the direction of the curve at any point evaluated along the curve. So you can see that it's going to move. The direction of this is going to be different as we go along here. So that's one axis. The second axis of this is going to be the normal. And the normal for a curve is governed by the curve tilt. So you can see that when I was tilting the curve before, I was rotating the deformation. That is because we were literally twisting the curve space along the curve because we're changing the direction of the normal. Now, if you know vector math, then the next part is going to be straightforward. We need to know how to build this vector. We're not given it by default, but we need to construct it. And then you can see, oh, well, we have these 3 axes. We have 3 axes. We just need to work out where the mesh sits within those 3 axes to create basically a coordinate space that we can map onto our curve space. It's a lot easier than you think, but at the same time, if you don't know how, it's impossible. So there's some steps that we need to go through here just to make sure that it's understandable. So I'm going to try and make this as clear as possible as we work through it. How do we do this then? Okay, we've got our Bezier curve. Here we go. So we've got our curves coming through. There we go. Now, if I have a sample curve node, which looks like this, then we get some information. The way the sample curve node works is it will sample your curves at specific factors. When we have this set to use all curves, then this is going to be a continuous 0 to 1 along, let's just draw a few splines here. 0 to 0.5 would be on this first one, and then 0.5 to 1 would be on that second one. So when we're using all curves, this factor is going to sample. If I put this to 0.25, then we're going to be sampling what is the position in Cartesian space, in the world of this point, what is the tangent at that point, and what is the normal at that point. Now, because this is geometry nodes, because we're using fields here, you can see the diamond sockets, you can perhaps imagine that if you have 100 points, and if each point was assigned a value between 0 and 1, then it would be able to sample each point separately, the curve, and it would be able to find out different positions. Think about that. We have a mesh. We are going to be able to assign values between 0 and 1 to the points of that mesh, and from that we can find out what the tangent and the normal value is from that. So this sample curve is basically 90% of the node group. Now, if we turn off all curves, then the factor 0 to 1 is just the factor along an individual curve, and which curve is defined by the curve index. So in this case, we have index 0, index 1, and both of them have a 0 to 1 factor along the length. Hopefully that's making sense. If you're new to this node, don't worry, you'll get used to it quite quickly. So now that we have our sample curve, let's have a little think about what we're doing, what we're going to use with our mesh here. So we have our cube. Let's just draw this out in here. You can see I've written just a few coordinates for these. So we can imagine we have our cube. The corner of it is on the world origin, and then we're 2 meters in each axis. If I wanted to work out what these positions would be in terms of our curve space, well, let's have a think about that. If I have a curve coming along, let's first of all define the axis of our cube that is going to be aligned to the tangent of the curve. In this case, we're going to use the z-axis. So what I want to do, if we think about our sample curve, I want to map a 0 to 1 value along the z-axis. So I want to normalize the z-axis. We can do this quite simply. Let's take our cube through a bounding box node. And then if I find the position, so let's read the geometry position, and I use a map range node, a vector map range, and I just use the min and the max from my bounding box as the from min, from max of our map range, and we map this to a 0 to 1, then what I'm essentially saying here is all of the positions of our cube, everything within its bounds, is now going to be mapped to 0 to 1 in all 3 axes. Now in our case, I'm only interested in the z-axis being aligned to our tangent, so I will use a separate xyz, and I can just take the z-axis here as our 0 to 1 value. So let's move this over. This can now plug into our factor. So create the normalized values, read which axis you're interested in as being your main axes. So great, now we've done our mapping in that direction. Now what I could do at this point is I could simply read the position for each point. Let's try this. If I take my object info, let's pass this up through a set position, and I'll just reroute this over the top. Let's take the position into our position on the set position, and we will have a look at the output here. So let's go back. Just because I'm using multiple objects to work things out, I'll do a little bit of organization. Let's press C to add a new collection. Put my cube into my items collection. I'll add a new collection as well for curves. And I'll drop that in there, and then I'll just hide them both. Fantastic. So if I select my geometry nodes object now, have a look in the 3D viewport, you can see that it just looks like the curve. If we want to kind of debug a little bit better, let's grab a utility math mix node, set this to vector, and I will just grab that position node that I had before. Let's duplicate that over, and I'll plug that into B. There we go. So you can see what's happened as I play with that factor. We're stretching our cube over the curve. Every single point is being stuck on to that curve itself. Now that makes sense if we come back into our sample here. So let's just move a few things out of the way here over to the right. Every single point in our cube is being assigned this factor, and that it's just being sampled to the position on the curve. So then what I want to do is I want to essentially re-inflate our cube, but rather than saying, well, what was in the x-axis is going to be pushed in the x-axis, I want to say what is in the x-axis is going to be pushed in the normal direction, and then what is in the y-axis is going to be pushed in the binormal. So how can we work these out? Well, to start off with, we have the normal here. So if I were to simply take the position of my cube points as they exist in 3D space, and let's have a look at them. I want to take my x-axis, so I'm going to separate x, y, z. Now if we draw this on the curve, if I have this little vector here, normal is normalized, so it has a length of 1. So it just means that if we multiply this by any value and offset it, the position, then we're essentially going to move in that direction, the normal direction, by the distance that we want to. If I take my x coordinate and I multiply it, so I take my normal here, I'm going to scale, vector math scale, by the x value. Let's just come back. If I simply, I want to add it to my position here, so let's add another vector math node. We'll add it like so. There we go. Now we can see that we have this ribbon. Let me just turn off my face orientation there. There we go. So it's pretty good topology. This is looking like what we would expect or hope to see. Now, the problem is that we have no vertical height here. I now want to take my y-axis and I'm going to scale it by the vector that is perpendicular or 90 degrees between the tangent and the normal. Now, to work this out, we have a very useful function. You don't need to know how it works, you just need to know that it's there. Cross product, take your tangent and your normal, like this. Plug this into your scale, and then we can add this one as well. Yeah, that's basically it. So because we're using the normal of the curve, what I can actually do, let me just make a bit of space here, is I can come into my curve and I can already Control T to tilt. And because the normal is defined by the tilt, and our binormal is also a product of the tilt, because we're doing that cross product with the tangent and the normal, so wherever the normal goes, the whole space is rotating around the curve tangent. And that is exactly what we see here. Now, I do just want to quickly turn on my face orientation. It looks like it's fine, actually. So what I was checking there is just whether we needed to flip the inputs of our cross product based on whether or not this was inverted geometry. You can see this is fine. When I flip it, it goes red because it's showing back faces. My apologies, we need to come back a little bit. I want to make sure that I'm adding to the position at the end. So I'm creating this like the rest of the information first, and then I'm basically stretching it along or offsetting it by this position along the curve. That is important because I want to also scale. So just after we've added our two scales together, I want to add another scale. And you can see if I scale this, we are now setting the radius. So I now want to know what the radius of my curve is because it's much easier to set the radius on the curve itself. So let's come back. How do we find it? It's not being sampled through our sample curve. Well, we also have this sort of arbitrary attribute that we can pass through. And what we will be passing through, if we search for radius, there we go. Now we can just plug this from the value socket into that final scale. And once again, let's grab our Bezier curve, make sure this is working. Tab into edit mode, select one of your points, Alt S, set radius. Control T is set tilt. Or if you prefer, it's in the N panel. If you press N on that properties, while you're in edit mode, select one of your handles. You can set the radius and the tilt in here manually. So that's all well and good. However, there's probably a few more things that we might want to add here. For example, let me just get rid of this mix. Don't need that anymore. We're going to start turning this into a node group just so that we have access to it in the future. And because we want to start thinking a little bit more intelligently about how we build tools to make them more modular, to make them more viable in larger node groups where you might want to have specific options exposed. So let's go ahead. I'm going to pull back my cube. I'm going to pull back my Bezier curve. I'm actually also going to pull back my bounding box, and I'll get onto that in just a minute actually. Take these nodes, so before your set position and after your object info and bounding boxes, Control G, put them into a group here. Let's tab back out. Let's just make these a little bit neater. And we're going to call this one Curve Deform Grouped, just like this. Now, calling it Curve Deform Grouped because if we use the accumulate field, for example, then we're familiar with a group ID, and this is essentially an integer assignment where different integers are grouped into separate computation. So if you have points with a value of 1, that is going to be computed separately to points with a value of 2. In our case, we're going to use that to define the curve index that we're using. So let's join a new socket onto our curve index. Press N, bring up our group tab of our information here, and we're going to rename this one to group ID. If we have a look at our other inputs, we have min, max, and our top one is going to be the curves as well. Now you never know what's happening outside your group. Sample curve node is going to need realized instances. So if you have created curves by instancing, then we are also going to want to just safeguard that by realizing the instances on the inside. I'm never sure how I feel about doing this with a tool, just because we're sort of implicitly changing the artist's meshes in a way which they don't necessarily know is going to happen. I think in this case it's fine though to do it. Also necessary. So there we go. So that is our inputs sorted. I'm going to come back to the group ID a little bit later because I want to show you how to use it. For now, we're just going to leave it defined as 0 because we're only thinking about a single curve at this point. If I tab back and if I just do a Control Alt, right click and drag, that gives me this mute. And we can see that the min and the max values are exposed. Let's neaten this up as well. Tab back in, press N, we're going to take our min value, hide, hide. There we go, and that's a bit neater. Now, the next thing that we're going to add here, just to give this a little bit more utility, is an axis picker. So you can do a custom axis, as in any arbitrary rotation. However, in our case, we are just going to be doing a single picked axis. So to do this, let's add, at least the way that I like to do it, let's add a new input, and it's going to be of type integer. I'm going to just move it above my min socket there. I'm going to rename it to axis colon x, and I'm going to use vertical lines here, y, or you could use slashes, and then z, just to make it clear that I'm picking 0, 1, 2, so my min and my max will be a selection between x, y, and z. And I'm also going to change my subtype here to factor, just so that as you move it across, you can see that you get that nice visual feedback that you're making that decision. Okay, great. Let's think about how this works. I'm going to need to put this in a couple of places because if we're using the z-axis as our kind of key axis, then we use x and y as our normal and binormal directions. So let's just duplicate our group input here. And I need to make a little switch to basically swap this out. Because if we're going to use x as our main direction, if we think about it like this, we have x as our main direction, then we're going to be using z and y assigned to our other two axes, but it's which order that we need to do them in as well. It's going to be a little bit testing here just to make sure that things don't go inside out. Let's take our switch node, utility, switch. We're looking for a float switch, and this is going to switch between x and y. And we're going to use another one to switch between the first one and z. There we go. Then we can use an equals node on our axes. When this equals 1, we want it to use the y-axis, Control-Shift-D. When it equals 2, we want it to use the z-axis. There we go. So this is our little switcher setup. Nice and straightforward, but it just gives us a very kind of intuitive way of choosing axes there. Now the same needs to be applied over here. However, obviously a little bit more complex because we have two going on, but let's just duplicate all of these. And I need to do something a little bit cleverer. Let's take our top two switches, Control-Shift-D, again, same Boolean values, but just separate. So if we're using X, then we want Y and Z as our false values there. So into these first two switches. If we have chosen to use the Y-axis, then we're going to be using X and Z as our new values. If we've chosen to use the Z-axis, then we're going to be using X and Y over here. There we go. And then we simply plug our switches up into where we have these scales. There we are. And I know it looks a little bit intimidating. There's a lot going on, a lot of crossed wires, but there's not really any way to avoid it. Might just collapse these, it makes them look a little bit less intimidating. And there we go. Let's just come back and let's make sure that this is going to work as we expect. I'm going to make sure I have face orientation turned on just so I see if it goes inside out. Let's go into my y-axis and z-axis. So z works, but y needs to be changed. So y is our value when it is 1, which is our true value here. So I need to make sure that instead of the z-axis going into the bottom one, it goes into the top. And instead of the x-axis into the top, it goes into the bottom, and there we are. That should now work. Fantastic. That's working exactly as we want. And maybe instead of a cube, let's try adding a Suzanne. Put this into my items here. Let's grab Suzanne instead. There we go, nice and stretched. Maybe we do an array of Suzanne. How about that? So let's pull this forwards. Let's just grab a mesh line. We'll do instance on points, Suzanne, and we will just realize this. Put it on like this. There we go. And maybe we just extend that a little bit. There we are. Okay, cool. So she's nicely twisted along the spline there. Let's make sure that everything's still working with our radius as well, and it is. If I go into my x-axis, you can see that that's twisting in a different direction. Sorry, that's the y-axis, and that is the x-axis there. Again, following off in a different direction. So this is what we expect to happen. This is working correctly. Group ID. Group ID is a little bit more complicated because it relies on us assigning min and max values normalized across a group ID. Now, I would say this is a bit more complicated, but I've actually already done a tutorial on this. So you can watch that tutorial if you want to learn how it works, or if you look down in the description, I'm going to include with this lesson file a start file for today's session, which includes the bounding box grouped node that we made in that tutorial. So if you just want to grab it and work along with the rest of this, then you can do so there. It will be clearly labeled anyway, and it will contain this node group that we made in that tutorial. There's a few things going on in here. You don't need to worry about them. But essentially what we have is a way to get geometry and a way to calculate the bounding box per group index, which we can then use with this curve deform grouped to assign a different part of our geometry to different curves. Let's see how we're going to do this. I'm going to just go into my Bezier object, and just for the sake of easy demonstration, you could be doing this procedurally, but I'm going to do it just by adding a few custom curves. There we go. Something like this is fine. This will do. All right, nice. So now I have 3 splines and they have an index, right? If we go into our Curve Deform group, we can have a look on our sample curve node. Each one of these has its own index. If we grab our bounding box here, I'm going to replace it with my custom bounding box like this. And we're just going to plug through our min and our max. And I do need to make sure that my geometry comes from this bounding box. Here we go. So still 0, 1, 2 in terms of our group ID being assigned. Everything is being assigned a group index of 0 at this point. I could actually make this a bit more interesting though. So if I take my realized instances, let's have a look at these, and I want to break this up into 3 sections. I'm going to do this, but the easiest way is going to be by index of my instances. So let's take an index node. So I'll zoom in here. I'm going to capture an attribute before my realize instances. It's going to be an integer because we're only interested in integers here on the instance domain. Let's have a look at this attribute. If I capture the index directly, it's going to go 0, 1, 2, 3, 4, 5, as long as this list is. And I'm just going to show you a little trick here for debugging integer values. Obviously with a viewer, it's just going to show white for everything above 1. And when we're dealing with integers, you have 0 and then you have everything above 1. So we need to make sure we can differentiate them a little bit better. Let's go ahead and add a texture, white noise texture. I'm going to drop this on here. I'm going to set it to 1D just to make it nice and light. And I'm going to recreate our viewer. And there we have it. So now you can see each one of these, if I turn off my wireframe, each one of these has its own color now. So we know for sure, we don't know what the value is, but we know that it is a different group. That's really all that matters. If I just take my index here and I divide by some value, then you can see that we're starting to break it up into different sections. And I can sort of push them all the way up to the top if I wanted. So now I know that I have 0, 1, and 2. Or I can infer that from the values. This is great because it means that we can simply take this value as our group index. Now, all I did was put that into my bounding box grouped, which means that everything is still using curve 0 from our Curve Deform. However, now it's being sampled along 0 to 1 in 3 sections. So everything 3 times over is being created along here. If I also use this capture attribute value in my Curve Deform group, then you can see that we're getting some real desirable results. So this is exactly what we're after now. So when the same group index controls our bounding box group index as well as our Curve Deform group index, then we're able to define which parts of which mesh go on which curve. Now this might all seem fairly abstract, so I apologize, but it's a workflow which is you're going to become more and more familiar with as you work with geometry nodes. You're going to need to be building these sorts of modular tools, and this is one from a tutorial months ago, this bounding box group index, but it enables us to do a huge amount now with Curve Deform being grouped. In the next tutorial, we're actually going to take this even further and do just a whole big tool and start thinking about professional workflows and professional tool building utilities, tech art, kind of being like a technician supporting your team of artists. What sort of thinking do you need to do to build these tools? And what sort of modules do you need? Because you're going to build up a set of these. And you can see from this little icon, I marked this one originally as an asset, and I would recommend that you do the same with your new ones. Because as you amass useful tools that are interchangeable and interoperable, you're going to start creating this essentially a vocabulary of skills with geometry nodes. Most artists are not reinventing the wheel every single time. They're using these existing tools. This is why I made ETK, because you just need like 100 additional low-level nodes to make geometry nodes like this really high utility thing, but you just need to keep adding them. And also you have all of the default assets as well that are now being shipped with Blender. And you can see that these are node groups. So everything is moving in the direction of these sort of modular, interoperable tools. And the quicker that you can learn how to make them, the faster you can accelerate your growth, not just with geometry nodes, but with Blender in general and with being an artist in general. That about wraps it up. Sorry for that little rant. This has been Curve Deform grouped, and essentially it's going to allow you to do whatever you want with building things and then stretching them along curves. Let me try and think of some examples here. Perhaps you're building a fence or a path or a road or a bridge or anything that you would draw with a spline, and you want to create, so for example, let's say you're creating a bridge. You have a number of modular assets. You can select them from a collection, array them, and then deform them to a curve. You can now say, I have 1,000 bridges in my scene. Rather than each one being individually created, they can all simultaneously, smartly create themselves and curate that out of my modular assets. And you know it's always going to work. Geometry Nodes is really cool, and I hope you enjoy it as much as I do. This has been fun. Hope you've learned something. I'll see you in the next one. Do I not normally say I hope you have fun?